Welcome to the second lecture of optimization class. As toward the end of the previous class, we alluded to possible solution of optimization problems by using graphical approach. We will continue that thought process and that idea in this lecture, and we will see that graphical approaches are very good intuitive approaches to understand many important concepts in optimization. In addition to that, they're also very important and sometimes could be used to solve problems which are two variable problems. If up to two variable problems, you can find solution using graphical approaches. But more importantly, they provide a visual and intuitive aspects of many important concepts in optimization that we can learn through these graphical approaches. So let's move on and see how we can take a optimization problem and solve that optimization problem using a graphical approach. So one thing before we begin, we want to limit these graphical methods to two variable problems. If there are problems which are more than two variables, then graphical approach might not be the best way to solve it, and that's why we need algorithms or other procedures to solve optimization problem that we will focus on later in the course. So caveat that we will be only using graphical approaches for problem up to two variables. So what I'm going to do here is I'm going to basically start with one optimization problem which is listed here. So recall we have an objective function, we have minimize, we have two variables x1 and x2, and the function optimization function is given by this fx, which is minus 4x1 minus 6x2. And so this is my objective function. And as we talked in the previous class, some of the optimization problems might also have constraints. So let's say this optimization problem that we are interested in solving has also a set of constraints, and here we are listed constraint g1, g2, and then there are constraints also on the variables. And let's discuss this. G1 is an inequality constraint. So you see this null, less than equal to sign, so it's an inequality constraint. Similarly, G2 is also an inequality constraint, whereas the constraint that are listed in the bottom, which is minus x1 less than equal to 0 and minus x2 is less than equal to 0, these are constraint on variables x1 and x2 such that they have to be positive, right? And that's where the non-negative null form comes into the picture. And so this constraint tells that x1 has to be always greater than equal to 0 and x2 has to be always greater than equal to 0. So let's talk through and let's go through different steps that are required to solve this class of problem, or at least this problem, in a stepwise fashion using a graphical approach. So the first thing that we need to do to solve a problem in optimization approach is we have to set up a coordinate system. So what we will do is we will use coordinate system and we will set that coordinate system and we will begin with that. So setting up coordinate system essentially means that since this is a two variable problem, I will be basically having an x1 axis and x2 axis, and then we will find out what is the origin, which is O here, which is the coordinate point that we are interested in, and this origin location, which is right here, this origin location right here is having a coordinate of 0, 0. Okay, so that's the first step that is taken, which is like coordinate setup. And then what we do is we go ahead and we generate scales along x1 and x2 variables. So what you have done is we have added 0, 5, 10, 15, which are equispaced along the x-axis, x1 axis, and similarly 5, 10, 15, and so on along the x2 axis. So these are essentially the scales that are added along x1 and x2 axis, and this process is basically setting up the origin and scaling and putting numbers on the scale so that we are able to solve the problem in a graphical fashion. Then the next step that is involved in this optimization process is we begin with plotting or graphing all the constraint function. Okay, and that's the important concept. Now we are focusing on plotting constraint functions, and at the first step of the graphical solution approach, we will be essentially focused on plotting all the possible constraint functions that are given to us. Now, The initial problem that we defined that has essentially 4 different constraint functions, right? 4 inequality constraint functions. Let's see how we can take that information that was given in the mathematical form in the optimization formulation and plot them as an constraint function on this graph itself. Okay. So recall the first inequality constraint or G1 was given by this equation x1 plus x2 minus 16 is less than equal to 0. So let's see how we can plot this function on this overall graph. So the first thing that you need to do, if you have an inequality constraint, then first using this equation, you remove this less than equal to sign and you create an equality equation. So which is given here. So I took this equation and I removed this sign and I equated this sign, and this becomes essentially, at least in this problem, it becomes an equation of the line. Okay, what I can do from this equation of the line, I can find out 2 points that lie on this line, and what it will allow me to do is to draw that line. So if I go by this simple reasoning that if you have x1, I can set this x1 equal to 0. Okay, if I set that, then I will have this equation x2 minus 16 equal to 0, or in that case x2 will be equal to 16. Right? So from there I can see that this solution where x1 equal to 0 and x2 equal to 16 leads to this coordinate system, and essentially this will be a point that will lie on this line. Okay, so we will take that and we will plot and we will put that and find out where that 0, 16 lies on our plot. So you can see we have now this 0, 16 is the first point that lies on this overall plot, and that is what the first thing that we will do. Now we will go ahead and we will try to find out a second point on this line so that we can draw that line itself. So using the same idea, rather than setting up x1 equal to 0, what we can do is to find the second point is I can set x2 equal to 0. So if this is 0, right, this is gone, x1 minus 16 is equal to 0. In that case, x1 is going to be equal to, this one is going to be equal to 16. So 16 comma 0 or 16 comma 0 will be another point that will lie on this line itself. Okay, so that gives me the second point on the line. So I will go ahead and plot and find out where that second point is, and that second point will be located right here. This is a 16, 0 coordinate, so that will be the one point that will be lying, and again we have 0, 16, that's the second point that is going to be lying on this line. So using this information, what we can do is we can essentially draw the line that represents this inequality constraint, which is x1 minus x2, x1 plus x2 minus 16 is less than equal to 0. So we'll go ahead, we will take these 2 points, 0, 16 and 16, 0, and connect those 2 points, and after connecting this point, we will get this line. Okay, now remember that this is an inequality constraint. Okay, whereas this is the line that represents this equation. So this line does not necessarily represent the equation that we have here. It essentially represents the boundary of this equation. In fact, only condition when it is equal to 0. So we need to represent less than equal to 0, and in order for us to basically find that and represent that information, we have to also go ahead and do another step. So that step involves finding out what we can do to find out which side of the line violates the constraint. So if we have less than equal to sign, right, like if we have equation like this, then equation, and if you have a linear equation, let's say x1 plus x2 and so on, well, essentially what that represents is one region, which is the line that we have, and one side of this line is going to be feasible and other side of the line is not going to be feasible. So maybe one side of this line is going to be a possible solution, whereas the other side of this line is not going to be the possible solution of this equation that we have, right? So what we need to do here is we need to find out which side is feasible and which side is infeasible. So this side might be infeasible because because of the constraint, whereas this side might represent feasibility, right? So what we will do is we will find out after plotting the line that we have which side of the equation is feasible. So one of the simplest things that we can do in order to find, at least for this one, that I will take this origin, which is right here, this point right here, which is 0, 0, and I will put that in the equation of the line that we have. Okay. So recall the equation of the line was x1, the equation of the line was x1 plus x2 minus 16, right, is less than equal to, or this was the inequality constraint that we are interested in. So what I will do is I will put this origin equation. So if I put that as as a value for x1 and this 0 as a value for x2, then at that location the function value, which is this function, the function that I have, which is function of x1 and x2, this function value will be equal to minus 16, right? So this is what I'm writing, the g1 0 0 function will be 0 plus 0 minus 16 and minus 16. Now in this case you can see that 0 0 lies on this side of the line, right? So the line is right here, but the 0 0 lies here. And if I take and substitute that point in my g1 equation, then that g1 value is equal to minus 16. Now minus 16 is less than equal to 0, right? Because minus 16 is smaller than 0. So that this point is essentially, or 0 0 point essentially is satisfying this equation. So this side of the line, and the point 0 0 lies on this side of the line, this side of the line the regions are going to be feasible. Whereas if I pick any point, let's say if I pick point something like here, which is let's say 15 20, 15 20, right, and we can write that, we can see that if the point is 15 20, and if I substitute that 15 20 in g1, okay, and if I compute 15 20 in g1, in that setting we will have essentially 15 plus 20 minus 16, and that is equal to 35 minus 16, right? So this is going to be, this minus 16, this is going to be essentially equal to 19. Now 19 is not less than equal to 0, and it is greater than equal to 0, right? So essentially if I take this point and substitute that in g1, that side is going to violate this equation, or in other words, that side is not going to be the feasible region according to this line. So from here what we do is we can see that the points which are lying above this plane or above this line essentially are leading to infeasibility of this equation, whereas the point which are lying on this side of the line are leading to the feasibility of this equation. So what we do is we basically take this line and we draw this hatches, which basically tells me that this region is infeasible. Whereas on the other side of line, this side of the line, there is a feasibility and that region is feasible. And that is the information that we plot for each of the constraints, especially if the constraints are inequality constraints. So that is my step 2 for at least the first inequality constraints that we have. Okay, so what we did here is we first plotted a line, and then by just doing a simple check on the putting a point on the either side of the line, whether that side is feasible or not, and then based upon that information we have basically marked which side is infeasible, and we have hashed that out by infeasible, marking the infeasible region. So instead of hatching, you can basically use also a shading. So here we shade this portion of the line. So we are telling that this portion or on this side of the line is infeasible, whereas this portion of the line is feasible. So that is, in a sense, is how you plot an inequality constraint in a graphical solution approach. Now we are going to repeat these steps for all the different inequality constraints that we have in our problem.